is that's called Greek letter phi. It's called phase angle. Okay, so today's class, what we're going to do is we're going to review some key transform features, and then I want to start though by doing a few earlier items with you just to make sure you've got those fundamentals in your head. And then in segment 2 we're going to talk about some new items called the amplitude, the period, and the phase shift associated with sinusoidal modeling, which could be either a sine or cosine function. And talking about in detail about what the period is of a trig function. And then when we get to segment 3, we actually want to do some data modeling with sinusoids, where we're now talking about things that usually behave as functions of time. So let's start with, let's say I gave you a point, and this is back in earlier at the very second or third section of the book. Let's say I gave you a point like 2, -3, and I want you to come up with the 6 trig ratios associated with the standard angle whose terminal side comes from the origin to this point. So first of all, always draw a sketch if you can. 2, -3 would be down here. And so here's where the terminal side sits. And what our standard angle then would be this angle. And what we want is we want the 6 trig ratios values associated with that location. So we're looking for then what the sine of theta is going to be, and the cosine of theta, the tangent of theta, and then the other 3. And you've done homework problems previously on this. I just want to make sure that I do one like this for the recording, and that some of you may still be having trouble with this. So what you want to always do with these things, as I said, is draw a picture and then label the coordinates there like I've done, and then label the legs of the triangle in there, the reference triangle. And then you know clearly that you have to get this hypotenuse here. So that hypotenuse length is going to be the square root of 2 squared plus a -3 being squared, and that's going to be 4 plus 9 is 13. So the square root of 13 is that length of that terminal side. Is this a unit circle? No, not a unit circle. This would be a circle, if you wish to draw it, that would have a radius of square root of 13 and not 1. Okay? Now, if we scale that back down to be our unit circle, square root of 13 is about 3 point something, right? So if I scale that back down, our unit circle would be, the point would still be here. I'm going to draw it a little larger than what it would be. That would be a 1, and then you'd have your ratios there, and so that little triangle you see right there with the same theta, except with a terminal side length of 1, those sides would be your cosine reading of theta and your sine reading of theta. And those triangles, that little triangle and this large triangle, are similar. So the ratios will still be the same. So we know that the sine definition is y over r at this point in the game. We all should know that. And so you look right there and you see -3 over radical 13. And then if I make an arithmetic error, stop me. Okay? Because we don't want any mistakes on our recordings, do we? Okay. And so we end up rationalizing the denominator, and we've practiced that a lot. That answer would be this then. Similarly, the cosine then is going to be x over r, and it's going to then be the 2 over the radical of 13, and you're going to rationalize it and write it as 2 radical 13 over 13. And then how are you going to do the tangent?
Sine divided by cosine.
Yeah, you could take the entire result you already obtained here for the sine and divide it by the cosine. Take that fraction you see, that big messy looking fraction right here, or in its previous form right here. See, here it is here as well. or take the y over the x, your choice. If you take the y over the x, it's negative 3 over 2. Now think about that before you just blindly believe what you wrote down. Everybody okay with that? Y over x, these three different ways of seeing it. You see here, look at this mess. If you multiply the numerator here and the denominator by radical 13, you'll lose it, and you get the minus 3 over 2. In a similar fashion over here, you see radical 13 over 13 reduces out numerator and denominator, and you get minus 3 over 2, or just y over x. The other thing to think about is look at this picture. That's fairly steep, isn't it? Isn't that more than 45 degrees down there? Because it has a steeper slope. And look at this slope, negative 3 over 2. That's bigger than negative 1 in a negative sense, right? So it fits with a sketch. Then, how much more work do we really have to do?
Not much.
Not much, because all we then need to do for our other three trig ratios is simply take the reciprocals of these. Now you should be pretty automatic on this. I wanted to make sure I went back over it though, because you'll probably see this on a quiz in a midterm and a final, okay? Because these are fundamentals. And so then if I wanted to pick up the cotangent of the angle, I'd just take the reciprocal of my tangent and I'd get negative 2/3. To get the secant of theta, I would take the easiest looking reciprocal of cosine form. It looks to me, see this right here? 2 over radical 13, isn't that easy to flip upside down? Form its reciprocal and get rad 13 right over there over 2. And then finally your cosecant reading of the angle is going to be probably grab this guy right here and take its reciprocal, so you get negative radical 13 over 3. Your 6 trig ratios. Okay. You could use your calculator if you wished, and use the inverse sine or cosine or tangent functions and see what that angle would be. And we'll talk more about that later this week, actually, a couple sessions from now. And what it's going to actually, the calculator will come back with, if you go inverse tangent, we'll get to this later though, because we haven't really talked about it yet. If you do this with your calculator, it's going to come back with a negative angle. A negative angle reading, which is going to be the reading you see right here. And that'll be explained a little later this week. Don't worry about that right now. Negative angle. Okay, let's do another quick review item. What if, can I erase the ratios over here? Okay. Here's another quick review item. Let's say I gave you, and this would be a problem in the book, I think like number 45 on page 393. If I give you a cosine of an angle and tell you it's minus 4/5, and I tell you that theta is in the third quadrant. Theta in quadrant 3. Does this match the problem in the book? Anybody notice? It's similar, okay? It's similar to this problem, okay? So you're given this trig ratio and you're in quadrant 3. So the way to do these would be start by doing what? Excuse me? Draw a picture. Very good. So I'm going to draw a third quadrant angle. So I'm going to draw my axes, and I'm going to draw myself a third quadrant angle whose cosine is, remember what that is? Remember, it's x over r. So the x in the third quadrant here, the x reading is clearly negative. And so that's where the negative 4 sits. And over r is your terminal side here, is your 5. Do you have to do the Pythagorean theorem to get this leg right here? Some of you might, but what do you know that it is? It's 3. It's a 3, 4, 5 Pythagorean triple, it's called. There are a multitude of those that show up in textbooks. A 3, 4, 5 is a right triangle called the Pythagorean triple. And this is a 3, but it has to be labeled how? Careful. Hint. What? Negative. Negative, otherwise you'll mess it up. If it was positive, it's going to be up in here or over here. Okay? Got to label those correctly. Now, the question I believe posed here is, what are the other trig ratios? So once you have this sketch, that's critical. Then you can start answering the rest of the questions. The sine of the angle, again, we just did it. The idea is the y over the r minus 3/5. Without doing any more math, hardly, what other two ratios can you get from these two?
The secant and the cosecant.
Perfect. The secant is the reciprocal of this cosine, so your secant of theta you'll be done with by just taking the reciprocal of that, minus 5/4. And your cosecant of that angle is going to be the reciprocal of the sine, minus 5/3. Right? Okay. And then finally, you need your tangent, don't you? And so what I would do is I'd look at this sketch, and I'd be able to easily pick up the tangent by thinking slope, or y over x off of that. And you can see it's going to be a positive 3/4, isn't it? Because the negatives reduce out. And you can see right here a slope, a positive slope, as expected. And your cotangent, finally, is the reciprocal of that. Okay, very important fundamental skills. Make sure you really have your trig ratios in your head. Let's see if we can do something else here. Let's review a touch on the transform idea, a little bit on the transform idea, which we've covered previously, but you still have confusion, I'm sure, about that. So let's practice. Let's practice with something like this. Y equals 4 cosine of 3x. Y equals cosine of 3x. Now I'm going to show you the way that I've shown you previously to do the analysis of this, or to understand the transforms and draw a sketch, but I also want to show you another way that you might really like. If we would take, here's what I've shown you previously. If we move this 4 over to the other side by dividing both sides by 4, we're going to see it this way. I like to call this what? The y stuff. The y stuff, okay? So this is the y behavior, and that 4, you know, does what to the cosine, the fundamental cosine?
Stretches it by 4.
Which way?
Vertically.
Vertically. Stretches it up and down by a multiple of 4. And as we've said before, look right here, cosine of this is your angle right in here. That's your angle. And so the cosine, you know, can never exceed 1 in value, can it? Or it can't get any smaller than -1. So you multiply those by 4, and that creates a range, doesn't it? A range for this function. This is a function of x. So you have a range showing up here of -4 to 4. Inside here, inside the cosine function now, is your angle. And if I take that 3 and tuck it down underneath the x, it goes down as the reciprocal of 3, doesn't it? And we've done this before, as a 1/3. As a 1/3. And I'm repeating myself from previous sessions. Over here, you know that your y behavior has been adjusted by a multiple of 4, causing a vertical stretch or amplification. Might as well introduce that word since we're going to talk about it later today. This is the amplitude. Amplitude. Now, you know that a cosine function has a period of 2 pi normally. 2 pi. And so, does it make sense to you that the behavior on y over here is similar in what you should expect to see over here in this algebraic structure on x? And the graph is going to be done what? Stretched out like a piece of candy? Like toffee or something, or rubber band? Or is it going to be squeezed? It's going to be squeezed if the mathematics works out properly. It's going to be made 1/3 as wide. So the period of this thing, and the book uses capital T, and other texts sometimes you see capital P for the period, is going to be equal to 1/3 of the fundamental period of this model. This happens to be a cosine model whose fundamental period is 2 pi. So it's going to be 1/3 of 2 pi. So you're going to end up with a period of 2 pi over 3. You want to be good at this, I hope. Okay, and we've done this all before. Let's see.
And then so you plot your first point at 2 pi.
Yeah, and then I'll help you here with the plotting in just a second. There's something else I want to do that ties into what's in the textbook, is what you're seeing in the textbook, and then, and actually I'm going to go ahead and keep it in this segment, is you see this kind of modeling in the textbook. And then what they will tell you for these sinusoids is that the formula for the period is 2 pi over omega. I'm trying to get you to not memorize formulas, although that's not too hard to remember. I'm trying to get you to understand the algebraic transforms that cause that to occur, because it's a little more sophisticated than college algebra. Okay, so we're trying to ramp up your the depth of understanding you have. Okay, so here's a formula, and in physics classes or engineering classes, you oftentimes see people grabbing this formula. Now here's the problem though. What happens if this model is, say, a tangent, a cotangent? A tangent or a cotangent model? There's going to be some other formula, isn't there? Right. But see, what's the fundamental period? You have, the fundamental period is 2 pi for what trig functions? Sine, cosine, and your cosecant and your secant, right? So the fundamental period of 4 of your 6 trig functions is 2 pi. So this formula, or this idea that I've shown you here, fits. But if you've got a tangent model or a cotangent model here, then you do the same. Think of the transforms. If this was the tangent sitting here, tangent here, then it would be a squeezed tangent graph, 1/3 as wide. But the period of a tangent or cotangent is pi. So you're going to take pi times 1/3. If it was a tangent, pi times 1/3, or pi over 3 for the period, if it was a tangent or cotangent function. Okay, yeah, question?
Is that t equals 2 pi over
Omega.
That just cuts to t equals pi over omega for a cotangent or a tangent?
Yes, yeah, that's what it'd be if you wanted a formula. Yeah, because see, this is the period of the fundamental, and what causes the effect is, this is really underneath here, it's a 1 over omega, analogous to what you see here. There's your omega, that's 1 over omega. 1 over omega. All right? So, any questions on these fundamentals of this kind of trig ratio material or the basics on these transforms before we go on to other stuff? What do you think? Making sense?
What he just said, tangent, cotangent.
The formula for the period is 2 pi over 3 or pi over omega or pi over.
Okay, let me just, here, okay, so these 4 trig functions in their fundamental form, you're comfortable with that. The period's 2 pi. If you have a tangent graph, let's say I have tangent of a times the tangent of some omega x. Look at the idea here. There's no difference than what I've just done with you on the other one, except the function is different. Okay, same transform structure. And so what happens is the fundamental period of your, this is going to cause a squeeze or a stretch by a 1 over omega factor. You might stretch it depending on the value of omega, one or the other. And so the period is going to be the fundamental period of tangent, which is pi, over the omega.
Thank you.
Okay. And same thing if that was a cotangent model. Okay. And the whole intent here, I keep saying this, the whole intent in this course is to get you so that you can use trigonometry for modeling real stuff, real things. And you'll be happy campers in applied other courses that you take where you have to use trigonometry if you can master these fundamentals. Okay, so let's go ahead and end this segment, and then we'll go ahead and get on to this next segment on amplitude, period, and phase shift.
Can we throw that up on a graph? No? The 2 pi over 3?
Yeah. Yeah. I'm going to go ahead and do that. I did it previously with you.